Okay, please check your attendance on the board. Okay. Before starting today's class, I will briefly introduce about the midterm exam. So we will take the midterm exam during the regular class time as announced in the syllabus, and then we will take the exam the next Tuesday. Okay, and then so this is the exam time, but so we need to arrange your seat. So please, show up earlier. So 15 minutes earlier than this exam starts time. So we will start exactly at 1:30 p.m. So please show up earlier. Okay. You will take the exam in this place. Okay, and then I believe it's okay. So we have about 76, and then this side has actually the other number 6. But I think it's okay. So we will and then the exam will cover chapters 1, 2, and 3. And exam will cover until we will learn until this class. Okay. So actually, in this class we will learn about the floating point numbers. Okay. And then the beta exam will cover until the floating point number. And then the exam will also make I don't know the exam in the exam I may ask about some information related to that assignment. Okay. Okay. And then this exam is the closed book exam. And then no electric devices are allowed. But you can use simple calculators. Okay. So actually in chapter 1, you may need to calculate the performance, right? And then in order to calculate the performance, so you may need to use calculator, right? So actually, so it requires multiplication and division, right? Okay, and then chain, so no chain, okay, and then you can answer in Korean, okay. So even though this is the English course, okay, but I believe most students are native Korean, right? So you can answer in Korean, so you don't need to answer in English during the exam, right? So, but if you are easy to use write in English, then you can use English, right? So you can answer in Korean or English. Okay. Any questions? No questions. So we are we are learning about the hardware. So actually, as I mentioned, in the chapter 2, in chapter 2, we learned about the instruction set architecture. So actually, we learned about the assembly instructions in our risk file. Okay, so this is actually the software part. Okay, so assembly code, it's the code, and then it's the instruction. So this instruction is given to a processor, and then actually the instructions need to be executed by processors. So it means that the assembly instructions are translated into digital data. Actually, it's a machine code, and then actually this is digital data. Okay, and then this digital data needs to be executed by hardware. So that's why, so from chapter 3 and chapter 4, and then chapter 5, and then we will learn about the architecture of hardware architecture of a computer system. So actually in chapter 3, so we are learning about some basic knowledge for understanding the hardware unit. Okay, so in the previous class, we learned about the adder. Okay, adder is required for executing add instruction. So so in chapter 2, we learned about add instruction, right? order to execute add instruction, we need to use adder, hardware adder. And subtractor is okay. But then we learned that we can implement a subtractor using actually adder. Okay. And then also you need to understand how multiplication is performed in hardware. Okay. And then actually it's simple. It's actually the multiplication of this the number is actually it's the same. It's the same to the multiplication of decimal numbers. Okay. We can generate the partial product. Then these partial products are just accumulated and then can generate the final answer. And then division is also the same. Okay. So like the decimal number division, you can also perform binary number division, right? But as I mentioned, division process demands comparison. And then based on this comparison result, we may need to perform subtraction or not. So actually, because the division requires this conditional execution, so that's why I said that division is more complex. So actually, the division is among the addition, subtraction, multiplication, and division. So usually the division is the most complex, the integer computation. Okay. So now we will learn the floating point. So then what is a floating point number? So it's a floating point, but it represents the floating point numbers. Okay. Then what are floating point numbers? Why floating point number system is required? So until this point, in chapter 2, just to remind that chapter 2, we learned about the basic RISC-V instructions, right? And then the basic RISC-V instructions include integer instructions, right? So like the RV32 I. So this is the basic RISC-V instruction set. So actually this I represents integer. So what is the integer? In Korean, it's 정수. Okay. So integer is just integer number, right? So actually, the basic RISC-V instructions support integer operation only, but our computer system also handle floating point numbers. So then what is the floating point numbers? It represents the non-integer number. So non-integer numbers. I think it's automatically fixed integer, non-integer numbers. So actually it means the real number. Okay, it's real number. Okay, then how can you represent real numbers in our decimal number system? So we can use the 1.2345, something like this. But there are some different forms of the representation. It's the normalized form or not normalized form. So normalized means that it's a decimal number system. So as you can see, the normalized form then is this number includes the sign. Okay, so we need to represent plus and minus of a number, right? So you need to include sign, and then the normalized form, the first digit is the non-zero number. Okay, and then actually is in this normalized form before this dot is a point. Then we have only one digit, and then this one digit includes non-zero, right? So this is the normalized. So 2 is the non-zero number. And then also there are some several numbers after the point, the dot. And then this number is multiplied by power of 10. Okay? So this is the normalized form. So this normalized form has the sign representation and one digit, the one non-zero number before the point, and then several numbers after the dot. And then this number is multiplied by power of 10 because the base of this decimal number is 10, right? And then this is the not normalized form. So as you can see, this is a 0. So because this digit is a 0, so this is not this is not a normalized form. Also, this example shows that before the point position, the dot position, you can find the 3 digits. So this is not a also normalized form. And then usually we can represent real numbers using this normalized form. Okay, so in the scientific calculation, the scientific notation, we frequently use normalized form of the decimal numbers, right? And then as I mentioned, it needs to include sign, and the first digit is a non-zero number, then several digits, several numbers at the point position, then actually the base is 10. So we don't need to use this. We don't need to store this data because the base is obviously 10. Then it's multiplied by power of 10. So how can we represent real number like this normalized form of the decimal number using binary number? It's the same. Actually, I said that I frequently said it's the same. The binary number system is actually the same to the decimal number system, right? So actually, the basic fundamental theory is the same. So this is the normalized form of the binary number. Right, it's the same actually. So as you can see, we need to represent sign bit of the binary number. And then as you can see, the first digit of this number is non-zero. And then in the binary number, non-zero is actually 1. Because in the binary number system, each digit has 1 and 0. So non-zero represents actually non-zero is 1. So this is always 1. The first digit of the normalized form of binary number is always 1. And then there can be several numbers at the dot position. And then in the binary number system, the base is 2. So it's power of 2. Then which information is required to represent the normalized form of binary numbers? This information is required, right? 1 is not required because it's already 1. This data is already 1, and we don't need to store this information, right? And then this part is required to be stored. Okay, and then this part. The base is already 2, so we don't need to store. Okay, this part. So this is the sign. This is called a sign. It's a negative sign or positive sign. And then what is this? This point, this number. This number is called a fraction. Because this number is represent the number after the that position. So this number is called the fraction. And then this part represents the power of 2. Then this part is called the exponent. Okay. So in order to represent the binary number, the floating point binary number, we need to store sign, fractions, and exponents. Okay, so those are required information for representing floating point. Okay, and then we actually in C, in order to store floating point numbers, so we use the float data type and double data type. So we will learn how many bits are required for float or double data type. Okay. So actually, the floating point number representation is standardized by IEEE standard. Okay. So actually, before this standard, actually every hardware vendors use their own floating point representation. That's the problem, right? So the problem is that our data stored by computer A cannot be understood by other computers, like computer B, because if the representation is different, then the other computers cannot understand this data. That's the problem. So actually, the floating point is specified by IEEE standard. So this is the standard number of the floating point. And then there are two kinds of representation. The single precision representation, and then it means this is, as you can see, the size of single precision is 32. So which means that in order to represent a single number, then we need to use the 32-bit data. Okay, it's 4 bytes. And then this is called the single precision. And then double precision is the double of the single precision. So this is the 64-bit, it's 8 bytes. Okay. So we can use the quad precision. Okay, quad precision recently 128-bit. But in this class, so I will just explain about the single precision and double precision. Okay, let's see how the floating point numbers are represented using this IEEE standard format. So, as I mentioned, now to represent a floating point number, we require sign information and exponent and fraction, right? So, and then obviously, these data can be allocated to the multiple bits in this number data. And then for the single precision, we need to use the 32-bit data. And then for the double precision, we need to use the 64-bit data. And then obviously, this information is assigned to the field of these numbers, number data. So actually sign has only two possibilities. Okay? So plus and minus. So we can just use 1 bit for the sign. So we double precision or single precision both use 1 bit for the sign bit. And then exponent is here. So what is the exponent? So plus minus 1 and then multiply to 2 x. So this is the exponent. So for the single precision data, the exponent occupies 8 bit, and then for the double precision data, the exponent occupies 11 bits, and then the other bits are assigned to fractions. Okay. So and then we can represent the floating point number x as the sign, using the sign and exponent number and fraction number like this. So sign bit, if the sign bit is 1, then means minus is a negative number. So it's minus 1, and then it's then followed by as, okay, it's a sign. And then actually fraction is the 1 point f, right? So it means 1 plus 0 point f, right? So this is the fraction part, okay? Because the first digit is 1, as I mentioned. So actually this is the 1 plus fraction, the 0 point f. And then the exponent part. So this is the exponent, and exponent is subtracted by bias number. So we actually, in order to represent the floating point number, we do not use 2's complement. So actually, as you can see, you can use the minus number for this exponent or plus number, right? Like the 2 to the power of 100. This is the positive number, and 2 to the power of minus 100. So this is the negative number. But the floating point number system, so we do not use, so you need to remember, we do not use 2's complement number for the exponent part. Okay, so this exponent part is just exponent minus bias, and then bias is also different for the different precisions. And for the single precision, the bias is 127, and then double precision, the bias is 10,023. Okay, so it's a different. Okay, so it means actually the exponent increase like this. So this is the exponent number, and then this is some value of the exponent. So actually for the bias point, so 127 for the single precision. So this number is actually same to the 0. Okay. Then if the exponent number is reduced, so it becomes the small number like the 0.00001. So it represents actually very small number. Okay? Even though this is negative, but it represents a very small number. And then if exponent is increased, so for example, after the 128, so it becomes the positive number. Okay. So it becomes very large number. Okay. So you can understand the exponent number like this. We do not use 2's complement because in the 2's complement number, the first digit is the 1. Actually, in the unsigned number system, so this is the very big number. Instead, we just in the floating point number, the exponent use the biased number system. So actually, for the different precision, we use the different biased numbers. Okay. So you need to remember this. Okay. So this is the example of the single precision. But you need to also remember that exponent all zeros and then all ones are reserved. It is those numbers are reserved for special keys. Okay. So actually, this equation is valid for the exponent is 0.00001 to 11110. Okay. If we use all zeros or all ones, then those cases are used for special case. Okay, so those exponent numbers are reserved for special cases. And then, so the smallest value for the exponent number is 0.0001. okay? And then it is actually, this is the bias, okay? So actually is equivalent to the minus 126, okay? Then what is the smallest number? So for the normal case, the smallest number is the, so as a magnitude, so sign is the same, okay? 1 point, and then 0, 0, 0, 0, 0, and then multiply by 2 to the power of 0, 0, 0, 0, 1 minus 127, it's minus 126. So this is the smallest number that can be represented by single precision floating point number, okay, for the normal case, right? So this is the equivalent to the 1.2 multiplied by 10 to the power of minus 38. The largest value, the exponent is the 11110. Then you can calculate like this. So this is the largest number. So because it's the 1.111111. So this is the 1 over 2, this is the 1 over 4, this is the 1 over 8, something like this. So, you know, if the this this digit is large, the number of digits is large, then it is close to the 0.1111. So this is a minor number. So it means the 1 over 2 plus 1 over 4 plus 1 over 8 plus something like this. So if this number of digits is large, it's nearly 1, right? So it's nearly 1. It's actually the 1 point f, so f, the largest f is nearly 1, so it's close to 2. So the largest value is approximately 2 multiplied by 2 to the power of 127. So this is the largest number that can be represented using single precision floating point number. Then double precision, then we can also, for all zeros, all ones are reserved for special cases. So we can also calculate the smallest value and then the largest value of double precision floating point number. So this is, so bias is different. So this is the smallest number and this is the largest number. So in this case, smallest and largest just represent the magnitude, right? Because we do not consider sign here, okay? I just explained the magnitude, okay? Then what is the precision? The precision of this floating point number. So the precision means that it's actually the exponent part just represent the power of 2, right? The precision is just determined by number of bits assigned to fraction, right? Fraction is fraction part. The precision is just determined by this fraction part. So for the single precision, we use the 2030 bit for the fraction bit. And then for the double precision, we use the 52 bit for the fraction part. So this is just the precision. For the single precision, the smallest fraction, the smallest precision that can be represented by this fraction part is obviously 2 to the power of minus 23. So it is because you know in the this is the fraction like the f just to represent the each bit and then f, and then the first f represents the 1 over 2. So it means actually 2 to the power of minus 1, and then this is 1 over 4. So which means the last bit of the fraction part just to represent the 1 over 2 to the power of to the power of 23, 1 over 2 to the power of 20, equivalent to the 2 to the power of minus 23. So this is equivalent to 23 multiplied by log 2. So it's equivalent to the 6 decimal digit. Okay, so it means, so actually, so this is the binary number. So in the binary number, so actually the the precision, the smallest number that can be represented by this fraction part is the 2 to the power of minus 23. But in decimal number, it's just similar to the 6 decimal digit. The 6 decimal digit after the point. Okay? So it is like it equivalent to 0.12345 for this digit. Actually, the precision is not high. It's not precise. Okay, so representing the real number. So for the double precision, it's equivalent to the 16 decimal digit. Okay, so it means that if we just represent a very precise number at the maybe if you want, so actually it can be normalized, but fortunately the numbers can be normalized. But if we want represent the number like 1.000000001, something like this, we cannot represent this number using single precision floating point. This is because using the single precision floating number, we can just represent the precision of until this position. Okay. So and then so let's see the example. So this example shows how to how to translate the decimal number minus 0.75 into the floating point number. So actually 0.75 is actually it's 1 over 2 plus 1 over 4, right? 0.75. So 1 over 2 plus 1 over 4. So actually we can represent this number like this. -1, and then this is negative, so it's a negative number, so it's a sign bit 1, and then the 1.1. So I said that in the floating point number system, the first digit before this point is 1, right? So normalized, so it should be 1. So and then this is the 0.5, and then so this is the 0.75. So it means, so we need to use the exponent as the -1. Okay, like the 1.5 multiplied by 1 over 2 is the 0.75. Right. So sign bit is 1, and then so in the floating point number, we do not store this part, we just store this part. So it is the 1 and 0.000. This is the fraction. And how about the exponent? Exponent is the -1, but this is the exponent is the exponent minus bias is the -1. Right. So exponent is the -1 plus bias. It's elementary school mathematics, right? So for the single precision, the exponent is the 126, right? Because 1 plus bias. And then for the double precision is the 1022. So for the single precision, then so it starts with the 1 because this is the sign bit, Then this is the exponent part. Okay, the 126 is the 0, 1, 1, 1, 1, 1, 1, 1, 0. Okay, so exponent part, and this is the fraction part. So the decimal number can be represented using the floating point number like this. And then this is the inverse example. So we can also easily calculate the decimal number in the floating point representation. Okay, this is the example. So this this is a single precision. So single precision occupies the 32 bit, right? The 32 bit, and then the first bit is the sign, and then the next bit is the exponent, right? So this is the next bit is the exponent, and then the next part is the fraction part. And then for the exponent, for the single precision, exponent occupies the 8 bit. Then you can just follow the standard of the this single precision. The first bit, sign bit, so it's 1. So it means it's negative, and then the next 8 bits. The next 8 bits are exponent number, right? So exponent is 1, and this is the fraction part. Okay, so fraction is the 0, 1, 0, 0, 0, 0, 0. So it means the fraction is the 0.01. So which means it's the 1/2. This is the 1/4. So which means 1.25. And then this is the minus, and then multiply by 2 to the power of. So exponent is the 129. So and then actually the real exponent is the exponent minus bias. So it means 128 minus 127, that is the 2. So it's the 2 to the power of 2. Okay, this one. And then if we calculate this number, it is equal to -5. So if we just know the representation rule, then we can just follow this rule. And then the normal number. So the normal, so as you can see, so this is the normal. So actually until this point, I explained about the normal representation. So it means that this, so exponent is from 0, 0, 0, 1 to 1, 1, 1, 1, 0. And then also I mentioned that all zeros and all ones are reserved for special cases. Special cases is the normal number. Okay, so if exponents are all zeros, so d normal, so d represents it's not, it represents not, and then so it means that it's not a normal number. Okay, it is used for representing special numbers. So, for example, so this is the case. All exponent bits are zeros. Okay, so actually you can think that if the whole exponent parts are zero, then it's really, really small, right? But in this case, we do not, the floating point standard do not follow the normal representation. So as you can see, it's different. What is different? Actually, it starts with 0, not 1. Okay, so for the normal case, it starts with 1, but for the if the all exponents are zeros, then you start with 0. And then fraction part. And how about the exponent? Exponent is just minus bias plus 1. Okay. So this is the so actually if the exponent is all zeros, then it is used for representing very small numbers, and then some very precise. Actually, small number represented it's close to 0, right? Because the magnitude is okay. So for these normal numbers, we use normal numbers for representing the numbers smaller than normal numbers. Okay. And then if the all fraction is 0, all fraction it's zeros, and then exponents are all zeros, then it represents the 0. And sign bit is okay. Sign bit can be 1 or 0. So if they actually put 0, the 0 we can say that the sign bit of 0 is 1 or 0, right? So it means that it can be plus, okay, it can be minus. And then any representation is okay in real numbers, right? So, actually all fractions are zeros, and then all exponents are zeros, then it is used for representing 0, real 0 of the floating point number. Okay, then there are two representations because of time b. So it can be 0, 0, 0, 0, 0, these are 0. Also 1, 0, 0, 0, 0, 0, these are also 0. Okay, and also if the exponent bits are all 1, then we can use also this case for representing special case. Okay, so for example, we may represent the infinite. So for the infinite, if the all exponents are 1s and then all fraction bits are zeros, then it represents the infinite number. So very large number. Okay, actually. Plus minus infinite. So which means it's a very large number in our system. Okay. So it can be calculated by computer hardware. Okay. So we can represent the plus infinite and then minus infinite. Okay. Because we can use sign b for representing plus infinite and then infinite and then minus infinite. And then if all exponents are 1 and then all fractions are not 0, so it's not 0. So if the all fractions are 0, then it is used for representing infinite number. But if fraction parts are not 0, it is used for representing not a number, NaN. So if you use Excel, the spreadsheet, and you may frequently find the NaN, so that represents the not of number. So it means, so we cannot represent this data using number representation. That is the representation of not of number, NaN. And then in order to represent this special case, we can set the all exponents are all 1, and then the fraction bits are not zeros. Okay, so it may be used for representing some irregular or undefined result. For example, divided by 0. Okay? So sometimes some computer system reports the exception if we use just if we just execute the divide by 0, but for some computers just report not a number for, for, for the result of divide by 0. Okay. So this is, so I just explained some special cases. We are going for all exponents are real or all exponents are ones. And then let's see some example of floating point arithmetic. So actually, so you may think that floating point arithmetic, so which means that the arithmetics using real numbers are just the more complex, right? The more complex than integer arithmetic, right? It is because, so for the floating point numbers, so we just use the normalized form, and then actually for the normalized form, in order to calculate the floating point numbers represented using normalized form, and we need to follow these 4 steps for floating point arithmetic. So this example shows the decimal number case, right? And then let's see why floating point arithmetics are just more complex than the integer arithmetic. Okay, and then it's just the decimal number. And then so actually, as I mentioned, the binary numbers, the fundamental theory or fundamental basis of the binary number system is actually same to the decimal number. So this is the example, and then this is decimal number. Then we want to plus add these two numbers. And what is the problem? For this case, this example, what is the problem? Exponents are equal, right? So firstly, in order to perform addition, then we need to set the exponent of these two numbers to the same exponent number, right? So we just set the exponent number, adjust the exponent number of the smaller number, okay, smaller exponent are here. So we just set the same exponent of these two numbers, right? And then we can just calculate the addition for the fraction part, right? Because the exponent part is the same. Okay, so firstly, we need to adjust the exponent part that make the two exponent of two numbers become the same. Okay? And then we can calculate this part, and then we can correct fraction becomes this number. Okay, and then we need to use the normalized form, and then as you can see, this result is not normalized. So we just normalize the result and then round the final result. Okay? So this is the required 4 steps for floating point addition for the decimal, and for the binary number, it's the same. So this is the example, and then what's the problem? The exponent parts are different. So firstly, we just adjust the exponent part of this number, right? And then we can calculate the addition for the fraction part. Okay, it's a significant. See, so then we can calculate we can get the result of this fraction part. So, and also, what's the problem? It's not normalized form. So we need to represent this number using the normalized form here. Okay. So this is the normalized form. Okay. So then there is no need to apply one up, one down in this case. Okay. So actually, for the floating point addition, and we need to follow these 4 steps. Okay. So what's the problem? More complex. So for the addition, so think about the integer addition, like a plus b. For the integer addition, then we can just perform some a plus b for each b, and then we can get a result. But for the floating point addition, then we need to follow these 4 steps for performing floating point addition. Okay, so problem is that the floating point arithmetic units are more complex, and then also it will take more time. It will take more cycles. Okay. Actually, the addition is very simple, and then usually we can get a result of two addition of two numbers very quickly within one cycle. Okay. But for the floating point number, we need to follow these 4 steps, and then actually the complexity of these 4 steps is each step is nearly equivalent to the complexity of one addition, or it can be more complex. So it means the floating point addition will take more cycles. Okay. So, so we may set a very slow clock for this floating point operation. But problem is that if we use the slow clock, what's the problem? Problem is execution time. Count, CPI, and then TC. So if we just use very slow clock, then it will degrade the performance, right? So that's why we cannot use slower clock. But because the floating point operation is very complex, and then in order to complete the floating point within one clock, then we need to use the very slow clock. So, but we need to avoid this case. Okay. So integer is very fast, integer operation is very fast, and then floating point operation is very slow. The problem is that, because of the floating point operation, then we also need to set up very slow clock for this integer operation, and then it will degrade the performance of computer system significantly. So floating point can be hyper. So we will learn about the pipelining chapter 4. So, and then actually basic idea is that we just split each operation, like this operation, this operation, this operation, something like this. And then this operation is complete within one clock, and then for the next clock, this operation is complete, and this operation is complete, something like this. So using the pipelining, then we can use faster plan, okay? And then for completing the entire step, then we need to take multiple clock cycles. This is the idea of pipeline. But we will learn about the pipeline later. So just remember that. So we can floating point be pipeline for using fast clock. Okay. So just remember that floating point is complex because of required steps. Okay. So this is the this slide shows the example from the architecture of floating point addition. Okay, then as you can see, so this part performs the step 1, step 2, step 3, step 4. Okay, it will take several cycles. How about the floating point multiplication? So, how about the multiplication? The multiplication, actually for the normalized number, the multiplication also needs to follow several steps. The first thing for multiplication, so we just perform the multiplication for the exponent part and then multiplication of the fraction part, right? So for the exponent part, you can just add the two exponent numbers, right? Okay. And then significant, the fraction part. The fraction part, you can just perform multiplication, okay? Normal multiplication, and then normalization, then round up, round down. And then finally, the sign bit is into mind. The sign bit is very simple, right? So minus plus minus multiplied by plus is minus, right? Plus 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 minus minus plus. So this is very simple. So this is the example of decimal multiplication, and also for the floating point number, the multiplication also follows the same steps about decimal multiplication. Exponent is just added, right? Because this is the exponent part. But we need to also consider the bias. Okay. So actually, this is not in the floating point representation, the exponent is biased. So actually, when we calculate the add operation for this floating point multiplication, then we need to consider the bias. Okay. And then significant, the fraction parts are just multiplied, then normalized, the up, not the down. Then sign B is actually very, very simple. So we don't need to consider what the sign complexity of the sign B. So actually, so this step is very simple. So actually, the floating point multiplication is also needs to take several steps. Okay? It means it is also takes several cycles, but the complexity is nearly the same. It's not exactly the same. The complexity is the floating point of the complexity of a floating point addition is nearly the same to the floating point multiplication. Okay. And the integer unit, the complexity of multiplication is more complex, much more complex than the complexity of addition. But in the floating point arithmetic, actually the complexity of addition is nearly the same to the complexity of multiplication. Okay. So if the unit just supports these operations, including reciprocal and the pure. Yes, some special functions also. The unit can also support those special functions. So usually, so actually, special scale root is performed by special function unit in CPU, also in GPU. So for the scale root, we just use the special unit. Okay? Then can be pipeline. So in so in chapter 2, we learned the RISC-V has 32 general purpose integer registers, right? From x0 to x31, right? So this is actually integer registers. Okay. How about the floating point numbers? Actually, so in order to support the floating point numbers or floating point unit, then we need to use the different extension in this file, right? And then usually in computer processors, floating point numbers are handled by floating point registers. So in RISC-V has the registers for floating point numbers only, and like the F0 to F31, right? So floating point numbers are just stored in the separate registers. The floating point numbers are not stored in the integer register file. It is stored in the floating point register file. Okay. Most processors, like Intel CPUs, also ARM CPUs, also use the different registers for the floating point numbers. So and then we can these processors can handle double precision or single precision. Okay, but if a processor doesn't support the double precision, so which means that the size of a single floating point register is 8 byte. Okay, so because it's 64 bit, and then for the single precision it's 4 byte. So, but as you can see, the floating points, we just use the same floating point register. So it means that if we handle the single precision value, then single precision value is just stored in the lower part of double precision floating point register. Okay, so because it just occupies 4 byte. Okay, and then for the load memory instructions, so which means that these floating numbers are also data, and then this data is in the data are in memory, and then for arithmetic instructions, then these data need to be transferred to the registers. In this case, the floating point number data needs to be transferred to the floating point registers, right? So this file also supports the FSW, FLD, FSW, FSD. The W represents the word, okay, it's 4 byte, right? Then D represents the double word, okay, it's 8 byte. And then the first F represents the floating point. So actually, if we use the FSW or FSW, then the target and source is changing. Okay, target and source becomes the. If we use the FSW, the target becomes the floating point registers. Then if we use the FSW, then the source becomes the floating point registers. Okay. And then in the risk file for the floating point arithmetics, then risk file just to support the floating point arithmetic instructions like append, observe, and mode, something like this. And then we can just represent the precision of floating point numbers using the postfix of the floating point instruction. So this part is called the postfix. Okay. So that S represents, I don't know, obviously single precision, and if we use the .d, then it represents the double precision. Okay. So this file also supports the comparison instruction at the FAQ, FLD, and then FLE, then S. Then branch instruction based on the condition. So this is the example. Then so this example just to handle the floating point number data. Okay, so the float is actually single precision, right? Then if we use the double in C, and it's the double precision. Okay. So as you can see, you can find some floating point instruction like this. Okay. But so in this course, actually, I will not ask about the floating point instructions because actually the main part of the is actually in chapter 2. So we learned about the integer instruction. So and then this is actually the main part of this course. So actually, I will just ask about the integer instruction in the exam. Okay. Okay. So, but the IPP standard just specified some many different standards about the floating point unit, but we can just trade off the complexity and then the cost of the hardware for implementing the floating point standard. Okay. Then I will skip the subroad parallelism. I will just handle this part in the chapter 6. Okay, so let's see some balance point, fallacy and peoples. So we learn actually this. So this is some frequently frequent mistakes in so sometimes we can make a mistake for uh, applying the shift operation. So it is because actually as I mentioned that we can use shift instructions for implementing multiplication and division, right? Because if we just multiply the number using power of 2, then we can apply left shift instruction or left shift operation. And then if we just divide a certain number using the power of 2, then we can apply the right shift, right? But problem is that if we just apply the shift operation for division, and then if we just apply the shift operation for the negative number, then the result can be wrong. This is the example. -5 divided by 4. So what is the result? What is the result? -1, right? So 5 divided by 4, right? It's -4, -1, right? But actually, we apply the shift operation for the -5, then it becomes -2. Because so this is the arithmetic right shift, right shift arithmetic, but it means that just 2 digits are just removed. Okay, so it becomes the -2. So answer can be different. So when you apply the right shift operation for the divisor, then this shift operation is to be applied to the positive number only. Right? So this is some common frequent mistake for applying the right operator, shift operator. So also another mistake is the association. So this is related to the precision of the floating point numbers. So we already know that this equation is same to this equation, right? Because this is the associative rule. Okay, so x plus y first, and then plus z is equivalent to the x plus y plus z, and then we can just first perform addition for the y and z. But x and y, x, y, z, just handle the very large number. X is very large number, and y is a very large number, and then z is the very, very small number. then what's the result? If we just perform this one, then result becomes 1, right? So it is because x plus x and y is the magnitude is very large, but just the sign is different. So we already know that this is 0 and then plus 1 is 1. Then how about this one? Problem is that we firstly perform y plus z. Problem is y is very large number. And then how about the z? Z is a very small number, 1. What's the problem? We cannot represent this precision using the floating point number. So y plus z is just y. What's the problem? Result will be incorrect. So this is just a problem. Okay. And then as I mentioned, with the floating point number, then floating point number has some restrictions for representing restrictions in precision. Okay. Sometimes even we already know that associativity is true in the real number, real arithmetic, but it's not true. It's not true in computer systems. Okay. So, and then also this is the very popular bug in the Intel CPU, the Pentium division bug. Okay, so I will conclude the chapter 3 because this is the arithmetic in computer system. So as I mentioned, we learned this part not because we firstly these hardware, so addition, subtraction, multiplication, and division. This arithmetic hardware is required for executing arithmetic instructions, right? So we learn many arithmetic instructions in this file. And then in chapter 4, we will learn how to build a processor. Okay, and then so in chapter 2, we learn the instruction, and then I just briefly explain, instruction is in memory, and then instruction is read, and then instruction is just executed, and then it generates result. And then in chapter 4, we will learn how these results, the result of the instructions are generated by hardware in more detail. Okay, so and then before moving to this chapter 4, we first learn how to implement the execution. And these execution units are required for implementing this hardware, okay, processing. Then it is required for executing arithmetic instructions. Okay, that's it. So this is the end of chapter 3, and then the midterm exam will cover until this chapter 3. Okay, any question? Okay, thank you for your attention. And okay, good luck for the midterm. 감사합니다.